Okay, factoring trinomials. Suppose we start with two binomials and we want to multiply these out. What do we get? If we multiply these out, we're going to, let's see, multiplication goes something like this: 2x times x plus 4, and then 3 times x plus 4. Here I'm using the distributive property to multiply instead of FOIL. If I distribute this one here, it will give me 2x squared plus 2 times 4 equals 8 plus 3 times x, and then 3 times 4 is 12. Combining like term, oh, there should be an x right here. This should be also 2x squared plus 8 and 3 is 11x, and then 12. Notice that we have here is a trinomial where the number in front of the square is no longer a 1 but a 2 or any other number. So the idea is to factor this. We want to factor this and return it to its original way it was. In other words, this is the factored form into two binomials. And of course there's been many ways of doing it. One of them, which I never really liked, was factoring by trial and error, and that never really worked for me. I hated it, and that's why I'm doing this. One of the methods that I learned was called the diamond method. Basically you start by taking the number in the front, multiply that by the number at the very end. So in other words, 2 times 12 will give us 24. Okay, be careful with that. The middle coefficient I just take and I write it down below. And the reason this is called a diamond method is because really you put it inside this box that looks like a diamond, and that's all. And then the idea here is to find the two factors of 24 that will add up to 11. So if I write my factors of 24 quickly, that's 2 and 12, 1 and 24, 3 and 8, and 4 and 6. Clearly, we can see that one of these numbers will add up to 11, and that would probably be, let's see, 8 and 3. 8 plus 3 is 11, so we're going to write 3 and 8. And then we can go ahead and put it into our parentheses, which looks something like x plus 3, and then x plus 8. However, notice it doesn't look like our original solution, right? That's because we multiply here by 2. So what do we do with that 2? So we actually just divide it back out, get rid of the 2, and 2 does not go into 3, it doesn't reduce, it doesn't divide, so we're just going to move it in front of the x. So it's going to become 2x plus 3. 2 goes into 8 evenly, so we're going to write x plus 4, and as you can see, that is exactly the solution we were looking for. Now let's take another example. Suppose we have now this one is not factored, so we're going to write it the way it's unfactored as a trinomial. So we get 5x squared plus 13x plus 6, and the idea is to come up with two binomials like so, and we start with our x, or diamond. I use the x without the box. So we multiply the first coefficient by the last coefficient. 5 times 6 is 30. The middle coefficient is just 13. And if we write our list of factors of 30, they will add up to 13. So I like to write them all out just to show. So 1 and 30, 2 and 15, 3 and 10, 5 and 6. As you can see, 3 and 10 are good candidates. So 3 and 10, we're going to write them in here. And then we can go ahead and write our x plus 3 and x plus 10. Again, because we multiply by 5, we undo that process here. So we're going to get 5 times x plus 3, and 5 goes into 10 evenly, so we can just write x plus 2. And if we multiply it back, go ahead and multiply it on your own. If you multiply it back, you will see that you will actually get this trinomial right here. Let's try one more. Now, sometimes they do not factor, and when you don't factor something, you can't find any factors for something, then we get something called prime. Here's an example of something that does not factor. So we get 2x squared minus 5x minus 2. You really can't tell whether it factors or not until you try. So what we do, we start with our first and last multiply into our x, or diamond. 2 times negative 2 is negative 4. Middle coefficient, negative 5. Now the factors of negative 4, they add up to 5. Well, let's see. 1 and 4, 2 and 2. If I were to use 1 and 4, I can get 5, right? If I can make them both negative. Negative 1 and negative 4 gives me negative 5. But negative 1 and negative 4, if I multiply them, a negative times a negative equals a positive. So that doesn't work. If I use 2 plus 2, I only get 4, not 5. So this is an example of something that does not factor. In fact, this thing is what we call a prime. This is prime because it has no factors other than 1. And then one more example just to cap it up. Let's see. Suppose you have 6x squared plus 15x. 15x, take away 9 or subtract negative 9. And again, we start by multiplying the first coefficient with the last coefficient. 6 times negative 9 is... before we do that, actually, there's a better way. Actually, if you look closely, all numbers here are divisible by 3. So if I factor out a 3, we can simplify this problem just a tad. So let's do that real quick. So divisible by 3, that means I take out a 3 and I end up with 2x squared plus 5x minus 3. We keep that 3 outside. That's also a factor. It's part of the problem. We can't lose it. And then we focus on the inside now. So again, 2 times negative 3 is negative 6. It's a lot easier than these two big numbers here. So negative 6, middle coefficient is 5. And again, what are the factors of 6 that can add up to 5? Well, we get 1 and 6, and then 2 and 3. Which of those two numbers will give me positive 5? Remember, the number here is positive. This one is negative. So if I add 2 and 3, I get a positive 5. But 2 times 3 is positive 6, not negative 6. So we have to use 1 and 6. So 1 and 6. Now how can I get a 5 here? Well, the only way to get that is to subtract 1. That gives us negative 1 times 6, which is negative 6, and negative 1 plus 6, which is positive 5. So that kind of works. So let's keep going. Remember, keep your 3. So we end up with x minus 1, x plus 6. Again, remember we multiplied by 2, so we must undo the 2, division by 2. 2 does not go into negative 1, so we just bring it up. It stays there, so it's going to be 2x minus 1. And then 2 goes into 6 evenly, so I get an x plus 3, and that is completely factored. Okay, I hope that helps.